right, recording is re-rolling. Okay, let's make some graphs. So we'll start with the changing out the mass. So who was the group who had the hearts to change out the mass? All right. So Liam, what were your what was your largest mass?
1,000.
1,000 grams. Woo. All right. So everybody see this graph on the top left says T versus M. That's time period versus mass. So you guys have done enough graphs in this class. You guys know time period, seconds, mass, and grams. You like that? Right? So Y versus X, T versus M. Okay. So we need to scale this up to 1,000 grams. Okay, that's kind of big, but yeah, we'll make it short. 0, let's go 200, 400, 600, 800, 1,000. Okay, so make this work. Squeeze real small here. Okay. And then what was your largest time period?
15 seconds.
All right. Then if I go ahead and divide that by 10, then I'll call that 0.5, 1.0, 1.5 seconds just for a single time period back and forth. All right. So let's plot some Cartesian coordinates. So let's go to your so let's go into that big one. Right, so 1,000 grams. How much time did it take to swing back and forth?
That was 1.5.
That was 1.5. Okay. 1,000 grams, 1.5 seconds swing back and forth. Right. All right. What was another mass and time period?
I had 300 and 1.42.
300 and 1.42. All right, that is right about there. Bam. Right, what was another combination?
200 and 1.409. 1.41.
Okay, it's right about there. Bam. That was another one.
150 and 1.44.
150, 1.44. Bam, right about there. That was another one.
100 and 1.41.
100, 1.41. Bam. Right. Do you have another one?
Yeah, it's the last one.
Right.
50 and 1.38.
50 and 1.38. Ooh. All right. So it looks pretty flat. Maybe it has a tiny upward slope, but it's pretty flat, right? Okay. And if you go from 20 grams to 1,000 grams, that's an expansion, what, like 50 times? So 50 times the mass, and over it was hovering about 1.5 seconds. Okay. So if you guys see basically a flat graph like that, what does it tell you the relationship between time and the mass? There's no relationship, right? Doesn't matter what the mass is, right? As long as it all is all in the bob, right? It should be the same time period, right? Now, having done this experiment in this lab enough years, I usually do actually see a tiny upward slope with this graph, and I think there's a good reason for it to be sloped up a little bit. Okay, and it has to do with the variable that we haven't quite got to yet, which is the length. Okay? Because think about this: if you have a small mass like this hooked on here, and then you replace that with this big guy, okay? You guys see if these are hooked to the same place, but their own center mass is at a different location. Okay. So if you take the little guy off and replace it with the big guy, wouldn't you effectively be lengthening the pendulum, making it a little bit longer? Right? And actually, if you do make the pendulum a bit longer, and some of you guys know this just from collecting the data that you just got, okay, that actually should affect the time period, which is why this might not be exactly flat, but ideally it would be a flat graph, and that's pretty well what it got. So we're good there. So whatever the master equation is that governs the motion of a pendulum has nothing to do with the mass of the bob. Okay. Next, angle. Who had a diamond? Well, it was changing out the angle. Who had a diamond? About Megan and friends. Do you guys have a diamond change out the angle? All right. What was the biggest angle you guys used?
90.
90 degrees. Okay, so I'll put theta in degrees on the horizontal axis. Go 0, 10, 20, 30, 40, 50, 60, 70, 80. Oh, looks like 90 will be a little bit off the beaten path there. All right, we'll do that. And what was your largest time period?
I think it was just 15 seconds.
Okay, so I'm going to scale this the exact same way I scaled the last one. So 0, 0.5, 1.0, 1.5, just like that. Okay. All right. Ah, yeah, thank you. All right, so I have it stated here. All right, so it looks like at mm, here for 30 degrees, it took 1.5 seconds. Bam, right there. 30 degrees over 1.5 seconds up. Okay. At 40 degrees, it was also 1.5 seconds. At 50 degrees, got 1.4 seconds. At 60 degrees, 1.3 seconds. 1 point, it's right up there. 70 degrees was 1.4. 80 degrees, 1.4. 90 degrees, 1.3. All right. Yeah, thank you.
Thank you.
Okay. Ooh. Hey, does that graph look also pretty flat, kind of like the first one? I think so. I think this is pretty close to horizontal line. Maybe slip down a little bit, but yeah, it's pretty straight across. Right? So you know what? I'm going to say that there's no relationship here too. Right? Yeah, whatever the master equation is that we're headed towards that governs, relates all these variables together. Looks like two of them actually had nothing to do with the motion. Well, at least at least not the time period, right? Okay. So the mass and the starting angle have nothing to do with how much time it takes to swing back and forth. Oh, that's interesting. Well, I hope length does, but you're gonna find out. All right. So who wants to volunteer their info for length? Length. How about Cole? Cole, you got some length data? What was the longest pendulum you guys used?
We used one that was 84 centimeters.
84 centimeters. So I'm going to put length on the horizontal axis, centimeters. And so the longest was 84. Let's see. 1, 2, 3, 4, 5, 6, 7. Oh, yeah, let's work. Let's go 5 centimeters at a time. So 10, 20, 30, 40, 50, 60. Yeah, I need this one. Yeah, thank you.
And we used
70.
we used length for Y in this one.
Okay. Yeah, got a length time period. All right. Okay. The time period in seconds on the vertical axis. So it goes up to about a second to swing back and forth. 0.5 right there. 1 point right there. Okay. So if you use each tick mark as like a tenth of a second, I think that'll be able to fit all the data in right here. Check this out. Right, so for 80, actually, look at this. Yeah. Okay, it's coming here. So 84 centimeters took 9.57 seconds. Bam, it's right there. 41 centimeters took 6.73 seconds. 6 point. Oh, so that was for 10, and then divide by 10.673. 673. That's bam, right about there. 20 centimeters took 478. 478. That's right. Bam, right about there. 10 centimeters. 0.355. 355. Bam. 24.5 centimeters. Took 0.517. 517. Bam. 11.5 centimeters took 0.38. 0.38. Oh, that's right about there. Okay. And 32 centimeters took 0.578. 0.578. Bam. All right. Yeah, thank you. All right. So, ooh, look at that. See how it's kind of slipped up a bit? Let me throw a ruler on here. Okay. Yeah, so definitely the longer pendulums took more time to swing back and forth. Okay. So next thing we've got to figure out is, well, what exactly is that relationship? Like at a glance, it might look linear, but then this is a situation we've run into several times before in past labs. Is if you think about it a bit, if you were to assume linear relationship and then you extrapolate backwards, see how there's this huge y-intercept? What that means is that for extremely short pendulums, like as it gets closer to like 0 centimeters in length, there would be some definite time to swing back and forth, which usually raises a red flag like, I don't know if that's maybe the relationship we're looking for. Hey, how many of you guys think this is probably hooks like this? Maybe something like a square root type relationship, like a hook. Ooh, because maybe 0, 0 would like logically be a point. You could go back and experimentally verify that like, empirically. Okay, but I think this is going to probably be more like a square root type relationship. So what we're going to do is we're going to manipulate one of these variables. Either we could square the time or take the square root of the length. Right? And if that plots out to a linear relationship, like time squared versus length, that might actually straighten out to a linear relationship. If that does, then this would in fact be a square root relationship. Okay, so we've done that before. But we only got a couple minutes till the bell. That's as far as I've been getting all my classes today. So hold on to this page. Oh, I forgot to mention it earlier, but you guys probably noticed there's another lab on the back. And also, we're technically still in first semester, so I'm not going to put any of these grades in until, well, end of the week, right? But hold on to this page because we still got to finish this lab and come up with the faster equation that's going to govern the motion of that pendulum. Okay. We'll do that first thing tomorrow.